So my name is Li, and I'm assistant professor from UIUC. So first of all, we know that machine learning has been ubiquitous in the world, which has been applied to many domains in our daily life to make our life more convenient. For example, autonomous driving, intelligent medical healthcare, smart city, etc. And also in more like safety critical domains, for example, malware classification, fraud detection, the machine learning has been applied to protect both personal and business information for us. However, so for my research, the main topic is looking at even such very powerful machine learning techniques, whether they can bring like severe consequence of like security and privacy concerns to our daily life. For example, in the real world example, since a lot of people like to ask what's the actual real world example, so here I want to show in 2016, the White House Associated Press Twitter account was hacked via phishing emails and spreading the rumor that the White House has been attacked, which like triggered the Autonomy trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within seconds. And this is just happens in real world in terms of fake news and what it can lead to. And as a human, we can see we should not be easily fooled by such fake news. But for machine learning and AI autonomous trading bots, usually they can be easily fooled in such an easier way. Although in the benign consequences or scenario, they are much more efficient and effective. And similarly, in Australia Airport, the biometric recognition systems have been developed for the safety screening, which has also raised a lot of safety concerns or privacy concerns. So that's why currently, even in the machine learning world, we have a lot of convenient platforms. A typical machine learner still have a very hard life to develop the robust or safe machine learning models or platforms. And that because we are still living in an adversarial environment, and therefore we need to come together and look at the adversarial strategies and understand what's the potential threats, and therefore to develop robust and machine learning, safe machine learning pipelines and models. And for adversarial machine learning, and people may ask the first question is what's exactly adversarial machine learning, and why? What's the fundamental question we are trying to address here, right? Although we have a lot of fancy examples online, we can see, but what's exactly like the fundamental reason causing such problems? So we know in the traditional machine learning approaches, usually people will assume the training and testing data from the similar or even the same distribution, right? And that's why we can train on one distribution and then make the test during the testing time. However, in the adversarial environment, either the training distribution can be manipulated in a way that we call it poisoning attack. Basically, it means that, for example, assume the recommendation systems, you can actually generate a lot of fake account on Yelp, for example, and then you can poison the recommendation, say restaurant or movie, to the potential customers. And or the testing data distribution can be manipulated, and we call these types of attack evasion attack, which means you can have a well-trained machine learning model on benign data, and you can protect it so that it cannot be, poisoned or in a way. But during testing time, the attacker can still find a way to manipulate the test data to evade the detection or to fool the model to make different predictions, right? So in this talk, I will mainly focus on the evasion attack and give some example of real-world examples of physical attacks and what's the additional challenges compared with digital attack and what's the tricks to make it more robust. And then I will discuss some potential defense principles. So based on the limited time, I won't discuss every detail about the work, but I hope I can present the principles so people continue with similar research or ideas or directions can follow the fundamental principles, which I think would be similar for different work. So first of all, let's look at the potential attack. So basically, let's take a quick example of deep neural network. So basically, we can see in typical deep neural network, we can minimize a loss function based over the parameter theta for the models, right? And given the training data X and Y pairs, taking the supervised learning as an example. And of course, since the deep neural network is non-convex, and we can do SGD and trying to find a certain local optimal. And this is what we typically do when we train a neural network. And when the attacker comes in, what the attacker can do essentially would be, as we know, the attacker would have an opposite goal with the defender, right? So basically, as an attacker, they may want to maximize the loss function by generating or optimizing epsilon, which is we can call it a perturbation, added to the instance, such that we can maximize over a perturbation, and this perturbation can lead to the maximum error for the certain loss function. And this can be viewed as an untargeted attack, because as long as this loss function is maximized, we view the attack to be successful. And of course, we can change this loss function a little bit to realize the targeted attack, and we can see that a little bit later. So basically, this is the adversarial perturbation, and there are several ways or many ways to optimize such perturbation. For example, we can use local search, we can use combinatorial optimization to optimize it based on if we have additional constraints for the perturbation itself. For example, the magnitude and the distance between x plus epsilon to x, right? And we can also use convex relaxation to find the epsilon given the geometry shape of the deep neural networks, and we can do the linear relaxation for activation functions, and then try to approximate the optimal perturbation for certain functions. And this is so far so good, and in terms of in the digital world, right? But we can see in the physical world, the situation could be a little bit different. For example, in 2016, the CCS work has already shown if there is optimized glass, if you can put this glass on anybody, and they can be fooled into other target person. So this is one as like a first physical attack, but you can see the human face still looks similar. And for like the face recognition cameras, usually they have a very relative good distance with human face, right? But whether it is true in the more like other realistic scenarios, for example, autonomous driving, and whether we can generate certain, say, adversarial road signs or adversarial objects on the road so that it will mislead the autonomous driving vehicles, that is unsure, right? So, and whether it is more realistic, here are some examples I taken from real world. Basically, one stop sign is taken near Vancouver and one is near Berkeley. So what we can see is that in real world, there are still a lot of graffitis and random patterns on different road signs. And that's actually raised the question about what if some of such patterns or graffitis are adversarial, right? And whether it is possible to have such adversarial perturbation or stickers or whatever thing can be captured by the camera perception systems of the autonomous vehicles and be misled for severe consequences, right? So before generating such physical perturbation, let's look at comparing with digital world, what's the additional challenges for it. So recall here, the goal is to generate some perturbation onto whatever sign, for example, a stop sign, the road sign, right? And then we hope the perturbation itself will be so robust that it can fool the, say, autonomous driving vehicles from different conditions. For example, in the physical world, there are different angles, distances, and lightnings, and so on. So how can we make sure the perturbation itself will be robust under different conditions? Because you can imagine if you have a perturbation here, if the lightning changes, your pixel pixel color will be changed, which is captured by the camera, right? And then the prediction based on the different pixel color may have different targets. And how could we make sure that is consistent? That is one challenge compared with digital world, because in digital world, the value of the pixels are very deterministic, right? And the second challenge is that, as we know, in the traditional adversarial attack in digital world, usually the perturbation magnitude is is minimized in a way that it will not cause human perceptual like notification. But here, if we want to say full autonomous driving vehicle, we actually hope the camera to capture the perturbation, right? So how should we improve or optimize the perturbation so that it can both be captured but will also be stealthy for human, right? And the third is, of course, against every physical work, there will be some like fabrication error. For example, if what you want is red, but ends up what you print out or obtained later on will be red or pink, right? And there are additional one, for example, in the digital world, you can add the perturbation everywhere, including some background, but in real world, it's impossible, right? So what we can do only is we can only generate perturbation onto the object itself. So how can we constrain such spatial, add such spatial constraint to the generation process to have the constraint optimization? So to address the following challenge, let's look at some detail about the method itself to see how each challenge can be addressed individually. So here is a quick recap about the digital adversarial perturbation. How do we do? So basically, as an attacker, we want to minimize, find the perturbation delta, do arguing over delta, which is a perturbation, such that we can minimize the magnitude of delta in terms of, say, LP null, right? And this is a loss function of any targeted machine learning model. And we hope the machine learning model can fool this perturbed instance, which is x plus delta, into some adversarial target y star, which is different with the ground truth x, right? So this is a targeted attack, slightly different with the untargeted attack we had before. And this is in digital world. And to address the first challenge, which is the different conditions under the physical world, we can update this loss function a little bit by considering a last loss function under taking expectation over different transformations or different conditions. So basically, what we have here is that you can sample the x, like here is x for single instance, and you can sample xi under different distributions, which can be called expectation over transformation. So basically what you have is different x are sampled from different distribution, which can representing like different angles, distances, lightnings, and color shifting, etc. And then you have the corresponding perturbation for the transformation, so that you will hope this optimize in a way that the perturbation delta itself will be effective under different transformations, and the kind of called the so-called universal transformation or universal attack, right? But it's under different transformation rather than under different against different images. And in this way, we will try to sample different distribution in a way to make sure the generated perturbation delta is effective enough under different representative distribution or transformations for the X instance to address the first challenge. And regarding the second challenge, which is we hope the perturbation itself can be stealthy, but still captured by the real world cameras on the autonomous driving vehicle, for example, right? So what we can have here is we can generate some mask of meaningful shape, and this shape will be called hidden in the human psyche, which means for the shape itself, it can be of like an apple or a Mickey Mouse head or things, so that the perturbation will be only onto the this region of the mask itself. And one interesting thing is that the mask cannot be arbitrary. So although the shape can be arbitrary, but the position cannot be arbitrary, because we know there are different regions or positions on the image that some places are more vulnerable than others. So if you happen to put the mask on the non-vulnerable regions, it will be very hard or almost impossible to generate the perturbation itself. That is to say, we can add a loss, for example, L1 loss to this whole loss function first, so that we can generate a sparse perturbation, random sparse perturbation. And then you will see where is the vulnerable regions. And then you can replace the L1 with L2 and TV loss or other smooth loss to smooth out the perturbation within certain regions, which you can place the mask onto the vulnerable regions and then smooth the perturbation inside the mask, so that we hope in the end, both the shape and the texture itself of the perturbation can be stealthy, that as a human, you may not observe it. And based on this spatial constraint perturbation, let's look at some examples like generated based on this method. So basically we can see here is different column shows different types of perturbation, and different rows shows different like physical conditions like distances and angles. And we can see on the first two columns, they are kind of like fading out to human, right? But all the stop signs in these slides are misrecognized as the speed limit sign 45 by a classifier. And the right-hand sign are misclassified as a stop sign. So this is a like targeted attack. And we can see we can either generate the mask as some fading out, or generate it as just some letters like love and hate, or some rectangle shapes. And I think many people are interested in the black and white rectangle shapes, since it shows that it's so easy to fool the machine learning model by attacking the stop sign, right? But one thing we want to pay attention is that the position of those rectangles are very sensitive. So for example, if the black one is just moved below a little bit, it may fail to attack. In addition, in another word, it means that the position of the vulnerable positions are very important, and also the white and black are not it's optimized. It's not like a default. So we optimize smooth it in a way that it becomes indeed white and black, which is showing some underlying property of the vulnerability and the road size as well. Okay, so this is a static analysis. Under we can see different conditions, the row size with perturbation or real world perturbation as stickers can fool the classifiers. And there are some people ask, like, for example, what's the dynamic examples, right? So if we really drive autonomous driving vehicle towards it, whether the sign itself will be vulnerable or not. And we can see here on the left-hand side, it's physical attack sign, one of the example in the previous slides. And on the right-hand side, it's a controlled experiment, which is a vanilla real stop sign. And if we drive a car towards it, we can see on the left-hand side, the caption always shows the speed limit sign 45, on the right-hand side stop sign. So the caption here shows the prediction of the classifier installed on the car. And here is the GoPro camera, which is not of very high resolution, but still can be fooled effectively. And similarly, with one different example of the physical attacks, the stop sign, and we can see still we get a consistent observation that the left-hand side is always misrecognized as the speed limit 45. So after this example, so there are some very interesting questions. For example, here is a model, the machine learning model itself is a classifier, right? And we know in reality, a lot of models used in autonomous driving vehicle and other real-world examples are using object detector models, so that you can automatically allocate the position of the objects. So the question comes as whether it is possible to fool the object detector models rather than the single classifier, which you will manually get a crop of the object itself, right? And I would say it is possible, but it is definitely slightly harder than for a single classifier. So basically what you can see here is if you have a stop sign with the perturbation here, you can see the perturbation here needs more colorful texture so that it can be effective. And you can see even all the other object can be correctly recognized. The road sign here or the stop sign here cannot be detected by this is a YOLO model. So with different angles and distances. And all the examples we mentioned above are white box, meaning we can directly optimize over the machine learning model, either it's classifier or object detector, and we can get a gradient and use SGD to search for the optimal perturbation. So one interesting example is whether such adversarial attack can be used to attack black box model, right? So if we do not have any access to the machine learning model, can we directly say transfer such attack to the black box model? Like basically we generate the perturbation against the white box model, say the YOLO here, and we can directly transfer it to say the another different, this is fast RCN, another different object detector model in a actually different environment and with the same perturbation. And we can see almostly consistent, the road sign itself cannot be recognized until you go to very, very close, and then the model itself detects the letters itself and it recognizes sign, but it's too late for a car to stop at this distance. So this is to say adversarial transferability itself is also a very interesting phenomenon, and we have several theoretical framework to estimate the upper lower bound based on the adversarial transferability and under what types of models it is more possible to prevent or encourage the adversarial transferability so that it can be successful in terms of black box attack or successful in terms of defending different attacks with ensemble models. So this is another big topic. I won't go to detail today, but I just want to show an example here. We can see in physical world, the adversarial transferability is very possible, and it's so effective that you even, for example, take the example of autonomous driving vehicle, you even don't need to access to the car model itself. You will have a high probability to attack the model itself. And this stop sign is so interested to the general audience, and people actually place it into the Science Museum of London and show, and people play with it under different conditions and show how effective it is in terms of generating the attack. And after the perception sensors, say in the autonomous driving vehicles, people ask, okay, we are actually having LiDARs, radars, and sensor fusions, and we actually, if the camera itself can be attacked, may not be that severe, right? So next, I want to give an example that even for the planar objects, such as stop sign, even though it's a real world object, but it's still flat, and we can put sticker onto it and take a camera, use a camera to take a picture of it. It's kind of like 2D, right? And whether it is possible for us to generate a 3D real world object and for example, LiDAR, such sensors, right? And also sensor fusions. So here is a quick example about it. So basically, this is just we used actually evaluate the attack against the real world LiDAR systems on the Apollo autonomous driving vehicles. And then this is just a quick pipeline. We don't need to go to detail about it, but I just want to show in the real world LiDAR detection pipeline, it's not a single neural network, right? It's a disconnected component with object recognition, feature extraction, and detection, and classification, and pre-processing, post-processing, like that. So it's not an end-to-end differentiable model that you can easily attack. But of course, we still approximate different component with the neural network. And essentially, it answers the question that whether we can use a neural network to approximate different components and leverage what we just mentioned as adversarial transferability to see if the LiDAR system can be attacked by real-world optimized object or not. So basically, we can see the goal here is we have an object, say it's a real world object like a box, right? We start with this regular size box and optimize the shape. Basically, it's a point cloud captured by the LiDAR systems, right? And we shift the points on of the point cloud in a way that it can be detected by the LiDAR system. The goal is that if we put the object here, the LiDAR will not detect it, even though it's of a large size with a regular object. And of course, the lights or the signals will be reflected because it's still object, but the object itself will not be detected by the LiDAR systems. And let's see, so the objective function itself will still be trying to minimize the distance. For example, in the 3D LiDAR here, we need to minimize the shaft distance or Hausdorff distance instead of LP in the image domain, right? And we hope the model itself can be attacked in a way that it will not detect this object. And by optimizing...
A question.
Sure.
Will unmute George?
Hi, Professor Lee. I just had a question. So in these examples, you're forming these adversarial components by you're solving an optimization problem. Is that correct?
Yes.
Can you give a sense of what the computational complexity for that optimization problem is? Do you have any sense of whether is it very, very hard? Do you solve it relatively quickly? I guess I'm just curious, for instance, could you solve it, for instance, in real time or something like that?
I see. So real time is impossible, but it's not very complex because real time, it depends on how large so that's why we start with a simple object. So it's a rectangle, so there are not a lot of points, and then you only need to shift the points in the 3D point clouds on the surface, right? And then based on the constraint optimization, I think in reality, it's complexity as a function of the number of points on your that you are allowed to shift. If you are allowed to shift every point on the object, then that's the dimension of n complexity. And in terms of the actual training time, I think it will require 1 hour about optimization. Yeah, because we have the constraint, the shifting should not be too large. If you can shift large positions, it can be very quick, but the shape will be very weird. So we need to find the kind of local optimal in terms of generating a reasonable shape. Yeah.
Thanks.
Yeah, thank you. Yeah, let me know if there's other questions. So basically, this is an example, and you can see on the bottom part, it's the object we just optimized. And if you drive a car towards it, the LiDAR will never recognize this object, although you can see the lines here, but you cannot see the detection of this box. But in the control experiment, we put the box of the similar size, and you can see on the LiDAR outputs, this box can be usually detected by this green box, but on the adversary example, it will not. And similarly, this attack, we want to show it is so robust that you can also place it onto different positions, not just in front, right? The same object. So it means it's actually a real world object. You can rotate it in a way as you want. So basically you can see similarly on the right hand side, it still cannot be detected by the LiDAR system, but on the control experiment, you can detect it with this green box. And there are other, also we can attack the sensor fusion by combining this together, like the shape and the textures, so that you can attack the sensor fusion system. And there are other shapes as well. For example, instead of start from the rectangle objects, you can also start from certain drones or like a circle or things. And more examples for different shapes and different attacks. You can look at this link with more examples. So the quick conclusion from the before mentioned examples is that we can see that adversarial perturbation are actually possible in real world, and under different real world conditions, it is very possible to attack different machine learning models. And next, I want to quickly go to an example. And for the example of attacking, so we have shown like attack the object itself, right? And here I just want to quickly show like we can also attack the environment dynamics instead of the object itself, which is also, you can say, maybe more realistic, meaning that you can say like change the like the weights of the autonomous driving vehicle or change the color of the wall. So in this simulation, we show if you change the weights of the car, and the goal is to let the car hit the wall, and then exactly you can achieve your goal by training this is a RL algorithm, and train the RL algorithm in a way that the car will eventually hit the wall by changing the body mass of the car. Basically, here the example I just want to show that it is possible to attack different positions or different components like the observations, the environment dynamics, the objects, or different like the actions and different places to generate such attack against arbitrary machine learning models. So next, I want to quickly just remind or discuss what's the potential defenses against all these attacks. So I hope all the examples I mentioned before can be convincing to show that all the machine learning models can be attacked in real world, and they are vulnerable in such a way, with different component and different strategies. Those models can be attacked, and according to this, many defenses have been developed, and there are mainly two like categories. One is empirical defense, basically trying to find the properties of adversarial attacks and try to defend against it. But we can see lots of such defenses have been attacked again by the strong adaptive attackers, which is a little bit a sad news for us. And the other big type or category is the theoretical certification defenses, which is good because it provides the lower bound of the accuracy. So it means that under certain conditions of the attack, it is impossible for the attacker to attack the model anymore. If I tell you the accuracy is 98, it cannot be lower than at 98, which is good. But the limitation for it is that such conditions are usually quite limited. For example, it can only certify limited radius of the adversarial perturbation. So in terms of that, I want to just mention one interesting like property of the data set itself, so that we can see how or what can be used as the potential principles to perform such defenses against attacks. So basically, we have a lot of min-max game we need to try to address, so that we can make some relaxation and certain things, so that we can certify the robustness. But they are relatively of high computation complexity. So whether we can leverage some cheap properties of the models or data itself to improve the robustness or detect adversarial attacks is a very interesting topic. And today I want to show it is possible. And actually the property itself is also very simple and interesting and also effective. So I want to mention it. So basically, we can see here, this is example of segmentation, which are highly used in autonomous driving, right? And then these are the adversary examples. You can see all the images looks like just benign to human, but then we can see they can be attacked into arbitrary target like Hello Kitty or single color or just a street without like any cars, whatever target you can have. But the question is, we know for semantic segmentation, it's the pixel level classification, right? And for each pixel, you can have your surrounding pixels or neighbor pixels to give the prediction for it. So we wonder whether after adding perturbation, your semantic segmentation like global or spatial consistency will be broken or not. So this is a key property we want to explore. So basically, we explore in a way that for each pixel j, we find all the neighborhood pixel, say m, and then compute the entropy of their prediction for the pixel j. So that means with higher entropy, it means the surrounding pixel prediction are very inconsistent for this pixel, right? And if it's low, it means it's consistent. And we want to see whether it is consistent compared for benign adversarial instances. And what we can see exactly is that if we draw a heat map for this entropy here, we can see for the benign instance, the entropy map or the heat map is very clean, right? The edges and everything is very clean. But for the adversarial instances, the image is that the heat map is very messy, meaning that after adding perturbation, even our human cannot see such small magnitude perturbation. The model itself will be messed up, meaning that their spatial consistency is broken. So based on this property, we have a very interesting strategy, which I think will be interesting to discuss, which is, for example, given the image, you can randomly like just capture or sample 2 patches with overlapped regions, right? And then you can put the overlapped region into a neural network or segmentation neural network to give the prediction. So the underlying assumption based on the previous observation is that for a benign instance, the consistency or the output of the overlapped region will be very high if we evaluate with MRLU, right? And if it's an adversarial instance, since the adversarial perturbation will break the spatial consistency, the output of the overlapped region will be very inconsistent. And as we show here, so and their consistency or their difference are very significant, and we can leverage such difference to train a model to detect the adversarial perturbation or adversarial instance. And the quick result is that in this row is like using this method, and different number k here means how many pairs we sample for the overlapped pairs. And we can see, of course, if we sample more pairs, the detection is like more robust, and it's almost 100% in terms of our AOC detection. And it's the amazing part is that it's even very effective against a strong adaptive attacker, meaning that if you tell the attacker what you are doing in terms of detection, the attacker can still cannot attack the model effectively because the randomness here, because the attacker cannot really capture which random pair you are choosing. So even they can also do random sample and make sure the overlapped region is consistent by adding another term in their optimization loss. But as long as those the overlapped region are not exactly the same with the defender, then they are not that effective. And also by optimizing that, the attacker's perturbation also need to increase, which is another drawback for the attacker. And this shows it lower down the reduce the attacker's ability, and also makes the defense itself very effective. And basically here, the conclusion is that we can use spatial consistency as an information to detect and improve the robustness of the machine learning models. And of course, people can ask, this is spatial consistency, there may be temporal consistency. Of course, we can leverage that to, I will not go to detail, but I just want to show example, like with temporal consistency, you can detect, like adversary video frames, in a video, and so that you can remove the adversary frames. So on the right-hand column, the video looks like good. And the temporal consistency can also be leveraged to detect, adversarial audios and other objects, as long as you think there should be some spatial or temporal consistency in your machine learning tasks. So with that, I will end my talk. I think I have 2 minutes. So basically, I'll show we have seen a lot of examples of real-world attacks, right? And mainly we focus on the evasion attack, but the poisoning attack is also very powerful. And also we can see if you are interested in the, say, like a poisoning attack, which is also can be also called backdoor attack specifically for neural networks. There is first work certified robustness against the backdoor. And also here is a link to provide all the defense, all the certified defenses against such attacks to show the state of art and unified platform that you can leverage different tools to compare with your certified defenses. So with that, I would say we still have a very long way to go in terms of defending against such attacks, and how to leverage different properties, how to do tight relaxation for neural networks so that to improve or certify the robustness of it. It's still a very interesting and open direction. So yeah, with that, thank you everyone. I'm happy to take questions.